Well, hello everyone. A very good evening. Myself Shatish. I'm the web admin of Kaziranga House, and I welcome you all to this revision session, the last one for this series of Quiz 2 preparation, which is focused for your subject of Mathematics 2. So, without further delay, I would like to invite your speaker, your guest for this session, your instructor, Mr. Prakhar Arora. I hope I'm perfectly audible to you, Prakhar Bhaiya.
Yes, Shatish, you are. Thank you very much.
Okay, so you can start.
Okay. Good evening, everyone. Thank you very much for having me. Now, for this session, we will be revising quiz 2. Okay. So, just a quick introduction about me. I am Prakhar Arora. I am presently in the diploma level, and I have been the teaching assistant for a few subjects. And last term, I was for the subject mathematics 2. And today I will quickly be going through the syllabus for quiz 2. And so yeah, the syllabus the I have planned the course. I have planned today's session like this. So first, we will go through the most important stuff for quiz 2, starting from week number 1 all the way to week number 8. And then I have planned to solve the last term's paper as well. Okay, so because of the time restriction, I won't be able to give you the time to solve each and every question, and then I solving the question. So how will we be taking over this session is, here I will show you the questions one by one, and I will give you 2 minutes to think over it. Okay, this time is not enough to solve the question, and to be honest, this is not meant for you to solve the question. The only thing I expect you to do in this 2 minutes is to find the approach. Okay, so first, to understand the question, and then to find the approach. Okay, so once you are through this, I'm pretty sure that you will be able to solve the question as well. So this is what I expect you to do in the paper solving section. And yes, so somebody asked for the theoretical concepts. Yes, I will be going through the theoretical concepts also in this first section of the session here. So here I will go through from week number 1 to week number 8 in the serial order, and I will be taking a few sample questions. Okay, not questions exactly, but when I explain you an important concept, I will share with you the segment of a question that is covered in this section. Say, for example, when we will be reaching the concept of let's say linear transformation. Okay, in linear transformation, there is a very important section of finding whether the transformation is 1-1 or onto. Okay, so this you have to see from just a second. Is the syllabus for week 2 5 quiz to 5 to 8 only? Just a second. Okay, please confirm is okay. Okay, so yeah, this saves a lot of time then. Okay, sorry, I missed this part. So it's from week number 5 to week number 8. Okay, so very good. Less burden on you all. Yeah, so this linear transformation, this is the topic from week number 5 only. Okay, so when we reach week number 5, we will find linear transformation, and then there would be a concept, there would be an approach to find whether the transformation is 1-1 or onto or both or none. Okay, so there I will not only tell you the idea, okay, or what do we say, the the logic here. Okay, I will first tell you the logic, and then I will give you a simple transformation. Okay, I will give you a simple transformation, and I will show you how we can predict, how we can claim that this is injective, surjective, or bijective. Okay, so I hope this is clear. Okay, this is how we are going to proceed in today's session. Okay, so before moving forward, is there anyone who has confusion in this part, what we are going to do? Okay, now anything here? Okay, now one more thing here, that I expect you all to be interactive during the session. Okay, I don't want this to be a presentation here. Okay, this is a live session. This is meant for us to interact. Okay, for you all to ask the questions where you where you are confused. Okay, point number one. Point number two, do not counter or do not intercept when other person is speaking. Wait for your turn. Okay, I would really appreciate if we follow the queue here. Okay, if you have a doubt, start by raising your hand. Okay, when I complete the topic, I will look over the queue, then I will approach each and every person there in the order. Okay, so let's keep it friendly, let's keep it good. Okay, yeah, so let us start. Okay, so week number 5. In week number 5 of Maths-2, there are two very important concepts. First concept that is introduced to us is null space. Okay, and the second thing here is the linear transformations. Okay, and both these, the questions on these two topics are very simple. Okay, but the problem is that these two are extremely abstract topics. Okay, maybe linear transformation is not that abstract, but null space is a very abstract topic, and most people complete the course Maths-2 and they move forward to machine learning theories and all, but they don't really appreciate the concept of null space. Okay, so it is very important that you pay attention to this, to the understanding of null space before you jump onto the questions. Okay, now here we are. Let's take a 2 cross 2. Let's take a 2 cross 2 matrix. Okay, I have a matrix. Okay, I have a matrix here. Okay, let's start from even before. Okay, let's start from here. Okay, we studied that linear equations. Okay, in week number 2, we had a topic of Gaussian elimination and all those things. There we had something like this: ax equal to b. Okay, and here a was a matrix. A was a matrix like this: 1, 2, 3, 4. Okay, x was a vector of variables. Okay, and b was the outputs. Okay, so this was like b1, b2. Okay, so what we did here was had we had a matrix. Okay, and then these were the variables, and these later form the equations: x plus 2y equals b1 and 3x plus 4y is equals to b2. Pretty simple. Okay, so this is where the origin of null space comes from. Okay, so let's see here. Okay, here we studied something, that whether this is solvable or not. Okay, whether the equation has solutions or not. Okay, and there were several rules to find consistency, inconsistency, one solution or many solutions. Okay, so this was the background here. Okay, now I want to change this equation a little bit. Okay, I want to change this equation a little bit, and this is here: ax equals 0. Everything remains the same here. Everything remains the same. I have the same matrix here: 1, 2, 3, 4, and I have the same variables here: x, y. with the only difference that my output matrix, okay, let's for the time being say output matrix, okay, and there is a reason why I want to call this as the output vector, sorry, not matrix, vector, okay, this is the output vector and this is the input vector. Okay, these are not the terminologies we began week 2 with, okay, but this is what we want to proceed with. Okay, later we are going to have topic of linear transformation, and there this will, all these things of input vector and output vector will start making much more sense. Okay, so yeah, now we have x as the input vector and 0 is the output vector. So this is the only change that we have. Okay, and if you remember, this also we studied there. Okay, this also we studied and we called it homogeneous equations. Okay, this is something we called homogeneous equation, and there was one very important thing that was mentioned. Okay, that either homogeneous equation. Okay, so before that, let me ask you a quick question. Okay, is homogeneous equation always consistent? Okay, let's not use this word. This is not in the syllabus for this quiz. Okay, so I want to ask you a question whether homogeneous equation always have a solution or not.
No. No.
Yes, sir.
Yeah, yes or no? Okay, tell me whether this always has a solution or whether this is always having a solution is not guaranteed.
Parallel lines don't have solution.
Parallel lines, actually, let's not go into that interpretation here. Okay, because it will take a lot of time, plus this is not in the syllabus for quiz 2. Okay, otherwise I did plan that for the session. Now this is yes. Okay, homogeneous equations always have a solution. Okay, now let me bring you to this thing here. Okay, if you remember that there were three possibilities. Okay, this was the chart: consistent, inconsistent. Okay, consistent had two further classification. Okay, unique solution, infinite solution, and inconsistent basically meant no solution. Okay, so this was the case for linear equations. Okay, this is for all linear equations. Either one of these three things will happen, either this or no solution. Okay, but homogeneous, for homogeneous equations, this is not a possibility. Okay, why is this not a possibility? Because you can always keep this vector to be 0 0. Okay, 0 0 is always a solution. Okay, and this is something that Sai Nikhil here mentioned. This is what we called trivial solution. Okay, this understanding here, this is the trivial solution here. Okay, and the reason we call it trivial is because this is always going to happen. Okay, that is where the origin of this word trivial means. Okay, why is this trivial? Because this is always going to be the case, and that is why we don't care much about it. Okay, so this is what we studied there. Okay, just a quick uh, brushing up of the old concepts. Okay, now so this is a homogeneous equation, and now we know that this will always have a solution. Okay, now this will always have a solution. Okay, so now why and how is this related with null spaces? Okay, let me write this equation here again. Ax equals to 0. Okay, let me write it like this. Ax equals to 0. X belongs to this, so Ax equals to 0. Okay, for the time being, this is a good enough definition. Okay, so what is this? Okay, well, everybody is clear with the set notations here. Okay, I assume set notation, everybody is clear. So basically, this is saying all. Okay, now if I write it in English, okay, it's very good that we when we write things in English, when we write mathematical terms and equations in English, things start making much more sense, and we are able to appreciate it more. Okay, so I have not written the left hand side intentionally. We'll fill it in a few minutes. Now on the right hand side we have this set notation here. Okay, now what is this? What is this telling us? Okay, this is set builder notation. Now what is this telling us? This says all values of x such that, okay, ax is equals to 0. This is how we represent, how any set written like this is interpreted, and I hope everybody is clear with it. Okay, so now we know that we don't have values of x here. Okay, we don't have values of x because this is a vector. Okay, so let's not say values of x. Okay, let us write a better definition, better words here. All vectors x, okay, such that ax is equals to 0, such that ax is equals to 0. Okay, and this is what we call null space of a. Okay, and this is null space of a. Okay, null space of matrix a. Now this is null space of matrix a. Okay, first of all, is this thing clear? Okay, is this thing clear here? Okay, now what is the implication of this? Okay, by now what we have established is, we have established that what is null space. Okay, null space is just a set of all vectors x such that ax is equals to 0. Okay, this is, let's complete this definition here. Let's complete this here. Set of all vectors, sorry, set of all vectors x such that ax is equals to 0. Okay, so null space is just a set. Okay, this is just a set of vectors that have a good property, that have an important property, that when they are multiplied with the matrix A, okay, when they are post multiplied, we all know that there are two multiplication in matrices. Either you can pre multiply a matrix or you can post multiply a matrix. Okay, so using multiplying with the matrix is not right here. We have to specify which multiplication are we talking about. Okay, so now this is basically what we mean, that set of all vectors x is that ax is equals to 0. Now why is this important and why do we need to study this? Okay, so one more thing here. Okay, so this, keep this definition here. Okay, keep this definition here. Okay, now let's jump to, there is a part here, there is a part of discussion, okay, that is pending here. Okay, and I will continue this. Okay, I will take this here after we talk about linear transformations. Okay, and in a few, after we start this discussion here, you will understand why I left this discussion at this point. Okay, so now let us start something altogether new, linear transformations. Linear transformations. Okay, now what are linear transformations? First let us study what are transformation. Transformation basically simply means change. Okay, changes, we can say this is just change. Okay, and what is the linear here? Linear is a mathematic, it is coming from the mathematical implications. Okay, that the degree of the change is 1. The degree of the change is going to be 1 only. Change is 1. Okay, this is not a mathematically sound meaning of linear. Okay, this is nowhere close to that meaning. Okay, linear in mathematical terms, this comes from the conditions of linearity. Okay, conditions of linearity, which we all have studied and we will revise in a few minutes. Okay, but we are not getting into the mathematics, we are trying to understand the topic here. Okay, we will come to formalism of mathematics later. Okay, so the linear transformation here means that we are going to talk about lines and planes. Okay, talking about lines and planes. Okay, and I hope that by now everyone understands that lines and planes are degree 1 equations. Okay, everybody understand? The equation of lines is the simplest line is y equals to mx plus c, and the equation of simplest plane is ax plus by plus cz is equals to 0. Okay, so if you see here, these are the variables here, x, y, and z. Okay, and here the variables are x and y. Okay, and you can see that there is no degree 2 term. Okay, what are degree 2 terms? Degree 2 terms are terms like xy, x square, y square. Okay, basically degree 2 just means, degree 2 means two variables multiplied. Okay, two variables multiplied. Here xy are multiplied, here x is multiplied with x, here y is multiplied with y. Okay, just one more thing, what is degree 3 now? Degree 3 means three variables are multiplied, so x cube can be a degree 3 term, x multiplied by x three times. Other term could be xy square. Okay, x multiplied by y multiplied by y. Okay, and we can also have xyz here. Okay, that is x multiplied by y multiplied, then it multiplied with z. Okay, so this is the degree 3 term. This we all understand, and we know that that this equations of lines and planes, this equation of line, just a second, this equation of lines and planes, this is a linear equation. Okay, this is a linear equation because the variables here are 1 degree variables. Okay, so this is why these changes are called linear, because here we are going to be dealing with lines and planes. Okay, this is it. Okay, now the second thing which I want to talk about is, okay, so we talked about linear here. Okay, that we talked about what is line, what is a plane, and what are the degree, why are they called linear, everything. Now what is this change? Okay, before understanding what is this change, we need to know what are we changing. What are we changing? Okay, so what is it that we are changing here? So we are changing vectors. Okay, what are we changing? We are changing vectors. Okay, what is the meaning of this? The meaning is that I have a vector v1. Okay, and when I apply linear transformation to it, it becomes vector v2. Okay, this is what a linear transformation is. Okay, and this is what transformation is, the changing one thing to another. Why is it linear? Because the degrees remain, because this is lines and planes. Okay, so this is what is happening here. In linear transformation, we are changing one vector into the other vector. Okay, now this is the basic understanding that we need here. Okay, now let us go into mathematics now. Okay, so to discuss the mathematics here, discuss the mathematics, I have vector v1. Okay, uh, I have a vector v1 and I'm changing it to vector v2. Okay, this may take a little time. Okay, but this is the very foundation of week 6, week 5, and week 6. Okay, so that is why even if it takes time, it is very important here. Okay, so we have vector v1 and we have vector v2, and then we are transforming it. Okay, just a quick connection again. Okay, how much do you remember functions here? How much do you remember functions? Okay, I'm talking about this function, f of x is equals to y type functions. Okay, if you remember this thing, you will be able to understand that there we had something like this. X was getting changed into y. Okay, for example, a simple function was f of x is equals to x square. Okay, what was this function look like? This function looked like 1 became 1, 2 became 4, 3 became 9. Pretty basic. Okay, but what is important here? Important is that a number is getting transformed here. A number is getting transformed here. A number is getting transformed here. Okay, and it is not just transforming in the air. Okay, it is, this number is given to a function and then the function is changing it. Okay, so this, there is a great resemblance, there is a sparkling resemblance between linear transformations and functions. Okay, and to be speaking truthfully, linear transformations are exactly same in spirit with functions from sets. Okay, linear transformations in linear algebra. Okay, I wrote here in spirits because it would be wrong if I, it would be mathematically wrong if I skip this word. Okay, so this, conceptually speaking, linear transformations and functions are the exact same thing. Okay, so whenever you get confused what is happening in this transformation, there is a very strong chance that if you try to understand it, assuming it's a function, you would be able to do it. Okay, this is how I did mathematics too. Okay, so this is it. This is what linear transformation is. And if you understood this, now understanding the mathematics of linear transformations is just a piece of cake. Okay, we don't have to do anything else. Okay, here now let's try to start making resemblances. Okay, start let's start drawing the parallels between linear transformation and function. Here we have a function that transforms this variable. Okay, so what is it that we are going to have here, that we apply to this number, that we apply to this number, sorry, this vector, that changes it? Okay, what is it that is going to change it? It is a matrix, a matrix A. Okay, how is it going to do here? Okay, let me erase this and write it exactly like it's on the left hand side. V1 getting to V2, and how is it going to happen? It is going to happen, this is it. If you understood this thing here, if you understood that this is same as this and that this is same as this, then this topic is done for you. Okay, so here v1 is the vector, v1 is the vector, v2 is the transformed vector, and a is the matrix. Okay, now coming back here. Okay, I said something about this here, input vector and output vector, right? And I said that this notation, this terms will come when we study linear transformations. Okay, and this is the time where we study linear transformations. Okay, so this is a v1, a v1 equal to v2. Okay, I don't want to use v1 v2 again and again. Now I want to stick, now I want to join, now I want to join it to the standard notations that we have, that ax is equals to y. Okay, usually it is written ax is equals to b. Okay, so now you can see why I wrote it to be the input vector and why I wrote it to be the output vector. Why? Because this is how we studied functions, this is how we learned functions. Okay, this is the input and that is the output. Okay, this is what a linear transformation is. Okay, now is there any confusion here? Okay, so what we did till now, okay, we studied we studied something about null space and we studied something about linear transformations, and we haven't completed any of these topics yet for our syllabus. Okay, so any confusion in this part, anyone? Okay,
No.
the topic we did till here is the very foundation of week 5 and week 6. If we are through this, then every topic is hardly 10 minutes long after this. Okay, we just need to bring the mathematical formulas and concepts here, and things will start falling into place. This was the foundation here. Okay, so if anyone has confusion here, please tell me, I will repeat. Overview of what, Yuvank? Okay, so can you be a little quick about it? Yuvank? Week 6, we haven't even started week 6 till now. Okay, we are still in week 5 only. Okay, no worries. Okay, so this is it. So what all we have done, uh, this is input vector. Yeah, okay, so this is it. uh, okay, now I want to draw another parallel from the functions thing. Okay, I want to draw another parallel from functions. Okay, now this was the graph we draw for functions. Okay, now here, but let's say y equals to x square, this was our graph. Okay, and so assume this is a nice looking parabola. So what happened here, these points here, they got transformed to these points here. Okay, now this is how we imagined a function to look like. Okay, this is how our functions look like. Okay, this is how we draw our function. This is our function f of x. Okay, how do we draw, how do we represent a linear transformation? Okay, how do we represent a linear transformation? Okay, and to be honest, representing a linear transformation is not that easy. For the very simple, there is a very simple reason that here, in when we are studying functions, our input is usually a real number, and output is also a real number. Okay, and a quick spoiler, when you enter week number 9 of this mathematics 2, this function here, the inputs are no longer going to be real numbers and the outputs are no longer going to be real number. So you will understand this very part that I'm saying, that visualizing functions will become very difficult when our input or output, or they are not in real world. Okay, they are not numbers. Okay, yeah, so this is the same problem we will have here, we are having here, that we cannot draw linear transformations very easily. Why? Because our input here is a vector and our output here is a vector. Okay, so what happens here is like this. Okay, so functions we wrote like uh, r to r. Okay, this is how we wrote functions there. Now how do we write linear transformations here? Okay, linear transformations are written like this: Rm to Rn. What is Rm and n? Okay, Rm means a matrix of order m cross 1, and Rn means a matrix of order n cross 1. Okay, so the change is, now the change is going to reflect here, that this is a vector here. Okay, this is a m dimensional vector, this is an n dimensional vector. Okay, so how do we represent this transformation here? Okay, this a, now how is this a going to fit here? Okay, a is the matrix of shape, where do I write it? Mm, okay, this we don't need anymore. Okay, Rn, and this is a vector of order n cross 1. Okay, and here we have a matrix A. Okay, and this m and n, these are not just any numbers here. Okay, they have great significance. The significance is that this is the order of the matrix here. Okay, just a second, this order is right. Let me quickly check it. N cross n. Okay, this is m cross n, so this this, so this is m, this is m, this is n, this is n cross 1, and this will be m cross 1. Yes, so this is a little change here, this is what is causing, this is n cross 1 is here, so this is n. Okay, this is n and this is m. Yeah, so this thing has to be, please correct the notations. Okay, this is n and this is m. Okay, I will tell you how to reduce this. Okay, So this is our matrix m cross n. Okay, so this is our matrix m cross n, and this is the meaning of the matrix here. Okay, let me write a matrix here. This is the complete shape of linear. This is the complete understanding of linear transformation we needed. After this linear no new logic is coming from linear transformations. This is the this is the end of linear transformation. That we have we have a vector here. We have an input vector here. Okay, this is an input vector. This is input vector, and this gets converted into output vector when we use a matrix. So this is my matrix here. This is a matrix. Let's make it 3 cross 2 matrix. Okay, so 3 cross 2 means 3 rows. 1 2 3 4 5 6. Okay, this is a 3 cross 2 matrix. Okay, now how can we tell which is the what is the size of the input vector and what is the size of the output vector? Okay, and questions like these do come in our exam. Okay, so here, now this is the matrix here. This is the order here is 3 cross 2. Okay, now how do I tell what is the input vector size and what is the output vector size? Okay, now start from here. We know that this is ax equals to b. Okay, and we know that x is input and b is output. Okay, now write the matrix here. Okay, sorry, write it like this. Okay, what is the order of matrix here? This is 3 into 2. Okay, now you don't need to do anything. You just need to apply the logic of matrix multiplication. Okay, now when is a cross I mean the multiplication of a and x possible? Okay, at the end of the day they are just matrices and vectors. Okay, when can you multiply the matrix a with x? Okay, you can only multiply them when this number is 2. Okay, when this number is 2. Okay, this is first thing is clear. Now we know that x is a vector. Okay, x is a vector, so anyway this size is going to be 1 only. Okay, now important is how I got this and how I got this. Okay, I got 2 because these two numbers have to be same for the multiplication to happen. Otherwise this won't be possible, multiplication won't be possible. And this 1 came from the fact that x is a vector. Okay, x is a vector, therefore this is going to be 1 only. Okay, and once you establish this, finding the size is not difficult. This is the input vector, and the output vector is going to be 3 cross 1 straight from matrix multiplication. Okay, now we establish something here, the size of input vector. Now this is the size, this is our matrix here. So if this is my matrix, what is it, what is the input and the output space going to look like? Let's say input and output vector look like this. Is from input vector is r2, input vector is r2, and the output vector is r3. And what is the size of this matrix A? This is 3 cross. Okay, and this thing is exactly what I did to check whether this was right or not. Okay, I had a feeling that I was going wrong here somewhere. Okay, and so I quickly just drew this thing. I just quickly drew this thing and I derived this. Okay, so this is what is happening here. Okay, so now you see what happens here. Now you see what happens. This is a matrix, and what will this matrix do? This will take a two-dimensional input vector. This will take a two-dimensional input vector, and this is going to convert it into a three-dimensional vector. I mean R3 vector. Okay, and this is linear transformation. End of it. Okay, this is the end of linear transformations. Okay, is this clear? Okay, now there are a few concepts of linear transformation that we have to study. That when is it one, when is it onto, and what are the image and what are the kernels. They are just 5 or 10 minutes at most. Okay, just two lines on each of those. Okay, so not difficult. Now I said earlier that I am stopping null space for a while. Okay, I said that as a part of discussion on null space I stopped, and I said I will tell you later why I stopped it. Okay, so now let us come back to it. Okay, let us come back to it. So let us rejoin this discussion. Yes, dear, I will do that as well. Okay, so this is a matrix. Now we have a new definition of a matrix. Okay, this I needed this definition of matrix. Okay, why I stopped here? Why I stopped? Because I needed you to understand what is a matrix. What is a matrix? I needed you all to understand that matrix is a way to transform vectors. I needed you to understand this, that a matrix is a way to transform vectors. Okay, and once this definition is clear, okay, and once this definition is clear, null space is extremely simple, just 2 minutes thing. Okay, let's take this I'm going to continue from here. Okay, that ax is equals to 0. Okay, so here we stopped at this definition, that null space of A is equal to x such that ax is equals to 0. Right, now what is ax equals to 0? Let's talk a little about this part here. What is ax equals to 0? Okay, ax is equals to 0. Okay, now see what is going to happen here. Okay, this, okay, I don't need this color. Sorry, I am a little particular about the way, about the colors I use. Sorry. So yeah, here, now here I have x. So first thing, this is the matrix that I have. This is a matrix. Okay, and there is a very particular thing in this equation. Very particular thing in this equation. The output vector is 0 vector. This is the crux of linear. This is the crux of null space. Okay, that the output vector is 0 vector. Okay, and this is the x here. Okay, this is the set of values which we call null space. Okay, now I said here, if you remember this, that null space is a set of all vectors x such that ax is equals to 0. Okay, I am going to borrow this from here, and I will make one last change here, so that we can conclude our discussion on this null spaces. Okay, now understand this thing. Null space of a, null space of a matrix A is equal to set of all vectors of x, oh sorry, all vectors x such that output vector is a 0 vector. This is the end of null space. This is that one thing which most students complete the course without knowing. Okay, when I introduced the topic of null space by saying that people can complete this course on linear algebra without ever understanding what this null space is. Okay, this is that thing. Take a time to digest this fact. Are things making sense here? Are things making sense here? Okay, right? Now this was about understanding the topic and everything. Okay, sometimes what type of questions come here from this thing? Okay, uh, dimensions of null space. Okay, so okay, now I said everything is just 10 minutes in week 5 and 6. Okay, let's start each of these topics. Okay, so the first thing that comes is dimension of the thing that comes here is nullity. Okay, now I don't think so in this class there is going to be any person who does not know that nullity is dimension of null space? Okay, please don't say that you do not know this thing. Okay, we call dimension of null space as nullity. Okay, now what is dimension here? What is dimension here? Okay, so dimension has a distinct meaning and distinct understanding in linear algebra. Okay, and since week number 4 is not in our syllabus, I will not dive into that. Okay, but I will tell you that generally, if I have a vector here, okay, if this is a vector, this is a vector 2 1, okay, this belongs to R2. Okay, I can say that this belongs to dimension 2. Okay, this belongs to dimension. Okay, so here an important thing, okay, sorry, I lost a track of thoughts. um, Sorry, this is the wrong heading, that is why I got confused. Okay, uh, sorry, the question that I was talking about is x belongs to Rn. Okay, this is the question that comes. Okay, sorry, I thought I wrote dimensions. This was my question, that the question can come in your exam, that what is, which subspace does the elements of null space of A belong to? This is the question that can come, that what is the subspace does the element of null space belong to, and you have options like R2, R3, R4, R5. Okay, and these could be any options. So basically what they are asking you is, they are asking you the size of this X. Okay, they are just asking you how many coordinates are there in X. Okay, now it should not be at all difficult for you. Okay, if I have a matrix of order 3 cross 7, okay, if I have a matrix of order 3 cross 7, okay, then what is the size of that X for which this is equals to 0? Yes, I will come to you. Okay, for this multiplication to happen, this should be a 7 cross 1 matrix, a 7 cross 1 vector. Okay, that means X belongs to R7. Okay, and this is the answer. Okay, I am preparing questions on the go, options on the go, that is why. So okay, so this is the correct option. Okay, this is a simple question. Okay, they can also give you that they can also ask you a question here, that which of the following vectors may belong to null space of A, without even giving you anything. Okay, they can say that A is a 3 cross 7 vector, is a 3 cross 7 matrix. Which of the following matrix do not belong to the null space of A? Okay, and they will give you sorry, which of the following vectors? Okay, they will give you vectors of different sizes: 7 cross 1, 3 cross 1, 2 cross 1. Okay, and then you have to answer this question without even knowing the matrix. Okay, so the question is never about knowing the matrix, it's always about knowing the concept. Okay, so such questions you can solve by this understanding. Okay, I hope this is clear. Okay, now let's quickly talk about dimension here. Okay, this is one thing which we understood. Okay, just a second. Now let us talk about dimensions. Okay, I will not talk much about dimension. Okay, I will talk only about nullity here. Okay, I will only talk about nullity here. Okay, nullity is the dimension of null space. Okay, this is the dimension of null space. Okay, and how do we find dimension of null space? Okay, so here I have a matrix here. Okay, null space is always associated with the matrix. So I have a matrix 3 cross 4, let's say any matrix here. Okay, and you have to tell its nullity. Okay, so I am going to state something which I will not prove in this session. Okay, here, that nullity is equals to number of independent, just a second. Uh, 0 1 0 0 0 1 0 0 0. This is these are independent vectors, and this is a dependent vector. This is dependent column. This is, oh, this is a dependent. No, 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 no. This is dependent variable. Just a second. This is a free variable. This is a free variable. Okay, and this is a dependent variable. Therefore this is the independent column and this is the dependent column, right? Okay, so this is a number, and this nullity is equal to number of let's say free variables here, number of free variables, and free is equal to independent. Okay, so the reason of this confusion is that I never write nullity, like I never study nullity like this. Okay, so that is why I do not remember these things on the go. Okay, but this is how we will solve this. Okay, nullity is equal to number of free variables. Okay, I never calculate nullity like this. Okay, how I calculate nullity is, okay, I calculate nullity from rank nullity theorem. Okay, rank nullity theorem. Okay, rank nullity theorem is very simple, it's very sweet. Okay, I have a rank, this is for a matrix, that rank plus nullity is equal to number of columns. Number of columns. Okay, and rank is equal to number of pivots in R R E F, and nullity is, okay, nullity, we don't need any definition for nullity, and this is just number of columns. Okay, so that is why whenever I have to write the definition of nullity like this, I always forget. Okay, and I also suggest you that you use this thing. This is neat and this is very less confusion. Okay, yeah, so this is simple. Okay, you are given a matrix, you are asked to find its dimension. Okay, what you have to do is just convert that matrix into the RREF form. Okay, and then let's do this. Okay, suppose I have a matrix here. Okay, suppose I have any matrix 1 0 0 0 1 0 0 0 0 0 0 0. Okay, I don't know what matrix I had earlier. Okay, but the RREF of that matrix, okay, but the RREF of that matrix looks like this. Okay, so my original question was find nullity of A. This was my question, find nullity of A. What I did, I converted that matrix A into the nulls, sorry, into the uh, RREF, into the reduced row echelon form. Okay, and here what do I have? These two are pivot columns. Okay, I hope there is no one who has confusion here. Okay, that implies rank of A is equal to 2. Okay, and it is very easy for us to see that number of columns is equal to 4. Okay, that implies nullity is equal to 2. Okay, this is how I calculate nullity. Okay, and this is, I think, the easiest way. Instead of doing free variable, independent variable, dependent column, this and that, this is a neat way to do it. Okay, so what is it? How do you calculate nullity? Nullity is basically non-pivot columns. Okay, non-pivot columns. Okay, for you all I did this thing. Okay, to just to show this I did this thing, otherwise I don't do this. I just see non-pivot columns, number of non-pivot columns, and that's it. Okay, and I hope this is clear. Okay, yeah, so this is done. Okay, so now just one thing here. Okay, we stopped this discussion at 5:50. Okay, this discussion of the concept of this foundations at 5:50, and it is 6 right now, and in 10 minutes we completed two very difficult things. What is the size of the null space here, and what is the dimension of nullity? Okay, so everything will finish in just 5 minutes, 10 minutes now. Okay, so this is indeed this first hour was indeed the heaviest one here. Okay, so is this thing clear? Okay, is this thing clear? Okay, now I think the discussion on null space. Yeah, Lawrence. Yeah. Okay, yeah. So somebody else also raised the hand earlier. Sorry, I forgot about that. Yeah. Any doubts here?
What is RREF, if you don't mind?
RREF, I cannot tell here. It will take very long. Okay, it will be in the wrong direction. This is
No.
the reduced row echelon form.
Okay. I only was known to like a full form because I'm confused of RREF.
Okay. Thank God. Okay, so this is very important. This is the reduced row echelon form. This is written as RREF. Okay, and if you are just looking at row echelon form, okay, row echelon form, that is REF. Okay, so just the short forms. Okay, and please, if anyone is there who does not know how to do this, please, you will not be able to do linear algebra, any part of linear algebra anywhere without knowing RREF. Okay, so please be a master at it. Okay, and it's pretty simple as well. Okay, so I think now null space is complete. Okay, so null space is done. Okay. Okay, so one more time, just before I end my discussion on null space, okay, let me just write once more. Null space of matrix A is equal to vectors. Sorry, let's write it like this. Matrix A is equal to set of all vectors x such that output vector is 0. Okay, this is null space. Okay, after 10 minutes I will be talking about something called kernel and images. Okay, and there we will use this definition again, just with one very small tweak. Okay, basically exactly the same thing. Okay, just the words will shift up down up down. Okay, is this clear? What is null space of A? Yeah, very good. So now let us talk. Yeah, anybody has any doubt? Okay, so now let us now null space is done. Let's talk about linear transformations. Okay, in linear transformations we know we have studied the transformations. Now let us talk about this thing, linear. I said that linear comes from the mathematical implications of linearity. Okay, now what is linearity? How powerful is linearity? What are the great implications of linearity? I'm afraid this is not the class. We can discuss that in detail here. But I will talk only what's necessary for the course. Okay, for the exam tomorrow. Okay, linearity means any function is called linear. Okay, any function is called linear if this is true. Okay, everywhere you will whenever or wherever you will find about wherever you will be talking about linearity, you will find this definition. Okay, this is the standard definition. Okay, and this is indeed the right definition also, but this is not the definition I like to teach the students. This is not the definition I think is perfect to teach the students about linearity. Okay, what I like instead is, it is also just the same thing, okay, here what we are doing is, this equation, this has two steps combined. Okay, this has two steps combined. That is why I am not a very big fan of this. Okay, whenever I have to use linearity, I use this thing because I am comfortable now. Okay, but when I have to teach linearity, this is not how I proceed with. Okay, instead what I do is I stick to this definition. I use this: f of x plus y is equals to f of x plus f of y, and f of cx, let's say cy, is equals to f of sorry, not f of, instead this is c of fy. Okay, now these were the two things that were hidden inside here. Okay, these were the two things hidden inside here. Okay, this is exactly the same thing here. Okay, if you try to elaborate this thing, what will happen is f of x plus cy will become, from this equation this will become f of x plus f of cy. Okay, you are basically splitting about here. Okay, and now this exact thing will come from here, and you will make it f of x plus c of f of y. Okay, as I said, exactly the same thing, but here we have two steps combined. That is why I don't like this. Okay, we will do this thing. Okay, and this is by no means a shortcut or by no means a trick here. This is exactly what linearity is, just that the steps are broken into two. Okay, we are taking things in chunk. Okay, so this is what linearity is. This is the mathematical definition of linearity. Okay, and you will see that only lines and planes obey this. Okay, you will see only lines and planes obey this. Okay, how this happens, this I will not teach you, but this is something you should know, that this linearity is only obeyed by lines and planes. That is why lines and planes are called linear, and spheres and circles and hyperbola, parabola, ellipse, they none of them do this. None of them like obey this. Okay, that is why only lines and planes are called linear. Hyperplane also. Okay, whenever I will say lines and planes, okay, I am implicitly talking about lines, planes, and hyperplanes. Okay, so if I omit that, just assume that I don't want to say it to save some words. Okay, so this is what linearity is. Okay, so what will happen in the exam? Okay, now I told you why this is linearity. I will not talk about what are the great implications of linearity. I will not talk about. I will just tell you one thing, that only lines and planes obey this. Okay, and this is the reason why we call lines and planes linear. Okay, so somebody asked about hyperplane. Okay, so see, Navya. Okay, see, this is the equation of line y equals to mx plus c. Okay, and this is the equation of plane ax plus by equals cz equals 0. Sorry, this is not 0, this is equals to d. Okay, and you know this equation can be written like this. uh, Let me bring this here. This will become mx, sorry, yeah, minus mx plus y is equals to c. Okay, which is basically, since these are all just constants, I can say that this is mx plus y is equals to c. Okay, so what is happening, what I want to talk here, what I want to say here is that this is the equation of line. Okay, ax plus by equals c is the equation of line. Okay, now I don't write this equation. Why? Because we are not habitual of seeing the equation of line as ax plus by equals to c. Okay, but indeed this is true. Okay, and if you can convert this equation in the form of y equals to mx plus c, where you will find the value of m in terms of a, b, and c. Okay, so this is equation of line. You can take my word for it. Now hyperplane, you can understand, you can find the trend here. Okay, now this is why I am writing this theta, because now I'm short of variables. Okay, I can take it t. Okay, so nothing different. Line has two variables, plane has three variables. Anything above three variables is a hyperplane. Okay, the condition however is that the variables are degree 1 variables. This is the condition. Okay, this is also a hyperplane. If I form an equation like ax plus by plus cz plus dw plus w, uh, let's say v is equals to p. Okay, this is also a hyperplane. Okay, we don't go about giving names to all the equations. We just say two variables line, three variables plane, above that hyperplane. Okay, so is this clear? Navya, is this clear? Great. Okay, so this is linearity. Okay, now what I want, what is important from the exam point of view is, what is important from exam point of view is to tell whether a given a given f is linear or not. Okay, this will be the question, whether when you have to tell that whether this is linear or not. Okay, so what you will be given is, you will be given f of xy is equal to some, I'm sorry, I forgot this equation definition. uh, xy is equal to, okay, this is, no, no, this is, I'm sorry, I forgot the question here. X plus y. Okay, so when we come to the questions, I will talk about that. Okay, basically what would happen here is, you will be given a function here. Okay, that would be f of x. Okay, and you would be given that f of x plus y is equal to, oh yeah, yeah, yes, 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 done. Okay, so this would be given to you. It would be a b plus m n. This is equals to p q. Okay, so this is how something will be given to you. Okay, and they will ask you to prove or tell whether this is linear or not. Okay, this is any variable mn o p q r q. Okay, so this is something like this, or in other form will be given to you, and they will say to tell whether this is a linear or not. Okay, or the question will be whether this follows linearity or not. In that case, you just have to check for these rules. Okay, what you have to do is, you just have to take one variable, oh sorry, one vector, and you have to take the other vector. Okay, and you have to add them like this, inside and then outside. Okay, I will take a question on this. Okay, I think I have a question on this in the question paper. Okay, so when this comes, we will talk about this also. Okay, so this is what linearity is. Okay, and all linear transformations obey this. So if the question is whether the given transformation is a linear transformation or not, so all you have to check is linearity. Okay, is this clear? Okay, is this clear? Now the last thing that I have is, and it is a very favorite from the examiner point of view, it is injective and surjective transformations. Okay, these are just fancy names. Okay, these are just fancy names. Injective means one transformations. Surjective means onto transformations. Okay, and one plus onto is called bijective transformations. It's bijective transformations. Okay, so this is exactly what the functions had. Okay, we had one functions, we had onto functions, and we had bijective functions. Okay, so this is what we are going to have here also for the transformations also. Okay, now important thing is that you remember these words. Okay, remember what is injective, what is bijective, and what is surjective, and what is bijective. Okay, because if you know this, the question is the same. Okay, it's just that you don't know the right word, you will lose marks for no reason. Okay, just remember these words. Right, so the question that will come is that you have to tell whether the transformation is linear or not. Sorry, whether the transformation is one or not. Okay, so what happens is, okay, we will come now, we are coming back to how to find this. Okay, how to find this? I will tell you extremely simple and extremely quick way to do this. Just do RREF of the matrix. That's it. Just do RREF of the matrix. It is that simple. When you do RREF, the answer is right in front of you. Okay, that is why, since this is so simple, the question often becomes difficult when the matrix is not given. Okay, usually you will not be given the matrix, because when the matrix is given, the question is hardly 30-second question, or maybe even 20-second question. Okay, so finding matrix is difficult in these questions. Finding matrix is difficult. Okay, now why I'm saying it's difficult? Sorry, not difficult. Finding matrix is main step. Okay, finding the matrix is main step. Okay, and this is exactly my next question after this, that how to find the matrix of transformation. Okay, so suppose we are given the matrix of transformation like this. Okay, suppose this is a very random matrix I drew in my brain. Okay, now here the question is that you have to tell it whether it's a one transformation, whether it's an onto transformation, whether it is both, or whether it is null. Okay, that's the question. Okay, so the questions would be, or the to find the questions, or the questions on this topic. Okay, so either this will be given, as I just said, either this will be given, or you have to find it. You have to find it. Okay, you have to find this matrix, and once you find this matrix, the steps are same exactly the same. Okay, so let us assume that we have the matrix somehow, either it's given in the question, or uh, we have drawn it ourselves by and how to draw it ourselves, we will look after this. Okay, so now we have the matrix. Just convert it to RREF. Just convert it into RREF. Okay, just do it with me. Mm, R3 minus R1. Okay,
R1.
so this will, sorry, one for this would be 0, this would be 5, this would be minus 2. Okay, or let me do it simply. Okay, R2 minus 6 R1, this is going to be 1 0. 6 R1 is 24. Okay, 7 minus 24, 15. Okay, 2 minus 30 minus 28. Okay, even if I do this RREF wrong, okay, the concept is what you have to learn. Okay, so this is 1, this would be, now I'm subtracting R3 minus R1. This is 0, 4 would come here, and this would be 5, and this would be minus 2. Okay, now let me erase this. Okay, I'm again saying, if I make any mistake here, okay, that is not the important thing. Okay, I draw matrices by myself in the brain. Okay, so this is nothing but natural. Okay, so this is 15. Okay, okay, so this would be 0. This is not an easy matrix. Okay, let me take an easy matrix. Okay, let me take an easy matrix. Let me take 1 2 3 2 2 minus 3 1 minus 2 0. Let's take the simple matrix. Okay, now let's just convert it into RREF. Okay, subtracting 2 here, this would be 0. Now this is 2 minus 2, 2 minus 4, this is 1, so this is going to be 6, this is going to be 0, 0 6 minus 2 0. Subtract 3 here, this is going to be 0, plus 6 here, this is going to be 3, and this is going to be 2. Okay, now, okay, now what I have to do is I am going to subtract this here twice. So what will happen is my 1 minus 2 0, this is going to be 0 0, and this is going to be 3 6 minus 3, so 1 minus 1 minus, it's going to be 4. So this is going to be minus 3, this is going to be minus 3. Okay, going to be minus 3, this is going to be 0 3 and 2. So what is happening is I am going to interchange the rows now. Okay, this is going to be 1 minus 2 0 0 3 2 0 0 minus 3. Okay, and this is a good enough point to stop. This is REF form. Okay, you can also stop at REF for this question. Okay, anyway, if you want to go forward, what you can do is you can make it 1 minus 2 0 0 1 2 by 3 0 0 1. Okay, I'm dividing by the necessary numbers. Okay, I have this here, and now you know that I can subtract here and I can subtract here. So anyway, my RREF is going to come 1 0 0 0 1 0. Okay, so this is it. I just did RREF. Yeah. Okay, so the RREF is 1 0 0 0 1 0. Okay, now why I did this? Now look at this rule. Okay, in RREF. Okay, in RREF, if all columns have pivot, if all columns have pivot, pay attention here. It is columns have pivot. So 1 1. Okay, this is 1 1. If all rows have pivot, this is onto. That's it. Okay, now there are proofs for this also, but I'm not going to get into that. Okay, this is it. This is how you have to solve it. Okay, now the question now, is this 1 1 transformation? Does all columns have pivot? Let's check. This column has pivot, this column has pivot, this column has pivot, so this is 1 1. This is 1 1. Okay, all rows have pivot. This row has pivot, this row has pivot, this row has pivot, therefore this is on. Okay, now what is the proof? I am not going to dive into it. That's it. Okay, now since this is both, this is also bijective. Okay, now I'm not going to take metrics here, it will unnecessarily waste time. Let me just take RREF forms. For example, suppose this is my RREF form. This is the RREF form. Okay, now the same thing, whether it is 1 1 or onto or not. Okay, now all columns have pivot. No, all columns do not have pivot, therefore this is not 1 1. This is not 1 1. Okay, not 1 1. All rows have pivot. Yes, all rows have pivot, therefore this is onto. Therefore this is onto. That's it, done. Okay, now the question is, this is the RREF form. Okay, is this 1 1 and onto? Let's check quickly. Okay, this is 1 1 onto, done. Okay, this is done. Okay, now in exam, since this is so simple, okay, uh, there are two variations here. Okay, first variation is that you have to find this matrix. Okay, the second variation is that this is given as a statement based questions. Okay, they will say if A is m cross n, okay, and m is less than n, okay, is A 1 1. Okay, the question will be that can A be 1 1? Okay, the question is, can A be 1 1? Okay, they can say A is m cross n and m is greater than n. Then the question will be, is then A is uh, A can A is guaranteed to be onto. Sorry, guaranteed to not be onto. Okay, so such questions will come. Now how will these things match? Okay, how can you solve this question, this type of questions from here, from this logic that I just said? Okay, now what you have to do in such questions is, you are given m cross n. Okay, take, you are given m cross n and such that m is less than n. Okay, so what you can do is, you can take m is less than n, 2 into 3. Okay, you 2 into 3, just create a simple rref. Okay, just create a simple rref. Okay, and the best thing is, that you make all possible, sorry, okay, sorry, you make a matrix, make a matrix with all possible pivots. The question is that you have to make a matrix by, and with all possible pivots. Okay, because the questions you will find here are, they will be, can a matrix be 1 1? Okay, so you need to find the possible, you need to find the best possibility. Okay, then here they think that a is guaranteed to not be onto. Okay, so you are talking about the best possibilities here. Okay, so that is why you have to first make the matrix. What will be the matrix? This is a 2 cross 3 matrix. Okay, and make it the best possible with best possible pivots. These are the best possible pivots. Okay, this is not looking neat. This is 1 0 0 0 1 0. This is the best possible pivot. No, this is the best possible rref. Okay, no 2 cross to 3 matrix can have a better this. Okay, now what is this? This can be onto, but can never be 1 1. Okay, simple, done, finish. Okay, so now the, what was the question? Now the question is, m cross n, this, can a be 1 1? No, a can never be 1 1. This is how you will solve these questions. Similarly, let's look at this question also. Okay, now what is the matrix here? M is greater than n. Okay, and don't choose high numbers. Okay, just take 2 3 1. Don't take 1. Okay, don't take 1, just take 2 3 only. Just take 2 3 and you will be sorted. Okay, let's take, for this one we want, a is 3 cross 2. A is 3 cross 2, so this will look like this. Okay, so what is the best possible matrix here with pivots? This. Okay, now the, what can this be? This is onto, no, sorry, this is 1 1, but never onto. Solve. So the question is, a is guaranteed to not be onto. Yes, such a matrix can never be onto. uh, Yes, yes, Moleswaran. Yes, for this 2 cross 3 matrix, okay, for 2 cross 3 matrix, okay, the matrix that you gave is 1 0 1 0 0 1. Okay, let's take this. Okay, now this matrix, when you do, this is not in REF yet. Okay, this will be RREF like this. Okay, now can you tell me, is this 1 1? Or is this onto? Okay, from here you can tell me that this is onto, but this is not 1 1. Okay, so this is the thing that we did here. Okay, and remember that I said, what is the best possible matrix that you can get? Okay, and this is the best possible matrix. Okay, when I say best possible matrix, I mean the matrix with maximum number of pivots, because this entire game is of pivots only. Okay, this is it. So this is how you will approach these questions. One last question I want to take from week number, this entire discussion is, one last discussion that that I want to do is, that is how to find metrics of transformations. How to find metrics of transformation. Yes, Riyan, sorry, I did miss this thing. Yeah, sorry. Thank you, thank you. So one thing is, uh, only square matrices can be both uh, 1 1 and onto. Okay, now do you need me to give you the reason for this? I hope not. Okay, now you can see for yourself that the only way that all the rows and all the columns can have pivots is when it is a square matrix. Okay, this is it. Very good. Yeah, how to find matrix? Yeah, okay. So this okay. So one thing, uh, Mulishwaran, did I adequately answer your question? Where you said, was this clear to you? Yes, very good. Now, quickly, this is a very important thing: how to find matrix of transformation. Okay, see this thing. Uh, this is my matrix A. Okay, now this is now we have entered week 6 and week 5 here. Okay, week 6 will be finished here. Okay, what is this matrix? What is the meaning of this matrix? Okay, now I'm going to tell you one more information here. And for this question we need an information. Okay, that A, sorry, here A is a transformation from A is a linear transformation from V to W. Okay, and the bases of V are B1, B2, B3. Okay, these are the bases, and for W, let's not talk about bases for the time being. We will look at it later. This is here. Okay, now here what do we have is, yeah, now what is the meaning of this? Okay, this is the information that I have. Okay, what all can I tell from here? What all can I tell from here? Okay, I can conclude from here that transformation, just a second, how do we write that? This is transformation of, just like this, linear transformation of b1 is equal to b1, linear transformation of b2 is equal to b2, linear transformation of b3 is equal. Okay, remember one thing, what will happen in the exam, what is this topic? Okay, what is happening here, that we are given three bases. Okay, we are given the bases for the input space. Okay, now everybody, I can use this word, right? Input space and output space. Okay, okay, so here what do I have is, this is the input space. Now we are given the basis of the input spaces. Okay, the basis, the first basis here. Okay, and now one more very important thing here, that these are ordered bases. Okay, now the entire discussion we are going to have, that will come, that will have ordered bases only. Okay, so here what is going to happen is, this is the first ordered basis. Okay, and its linear transformation is v1, its linear transformation is v1, and that is the first column here. The linear transformation of the second basis is v2. Okay, similarly the linear transformation of the third basis is v3. Okay, this is how the question can come. Okay, they will say that the basis, they will say that for v, bases are 1 2 3 4 5 6 7 8 9. Okay, and they will say that transformation of 1 2 3 is, yeah, this is what I was missing. This is the projection, this is written like this. Okay, there was no problem in writing it lt. Okay, but standardly it is written like this. Okay, I was missing that. Yeah, yeah, so here this is the question will say that this transformation looks like this. Okay, 4 5 6 is equal to 0 0 1, and they will not say it like this. They will say transformation of 7 8 9 is equal to 1 0 1, and then they will say transformation of 4 5 6 looks like 0 0 1. Okay, and they will say you have to either tell you have to find the matrix of transformation, or you want to tell the one or onto of the transformation here. Okay, so how can I write the transformations here? Okay, how can I write the matrix here? Let me write the matrix A here. Okay, so first, what is the first ordered basis that I have? What is the first ordered basis that I have? 1 2
Zero
3
1
and
0.
what? 0 1 0. Exactly, this is 0 1 0. Then I have 1 0 1. Then I have 0 0 1. Wrong. Okay, this is wrong. Okay, this is wrong because order has been changed. Order has been changed. Okay, this mistake happens in the exam. Okay, they will change the order here while telling you this. Okay, so don't make this mistake. Okay, the question for the one onto will remain the same here also, but telling the transformation matrix would be changed. Okay, so don't make this mistake. So then it will be 0 0 1 0 0 1, and then the last thing would be 1 0 1. Okay, now here you can see that it is both 1 1 and onto, right? It is both 1 1 and onto. You can check it yourself. Okay, just subtract, just make it minus here. This will become 0, this will become 0, and this is just a linear, this is 1 1 onto both. Okay, so this is how you can find the transform, this is how you can find the transformation matrix. Yes, Lawrence.
So, sorry to interrupt, but can you please repeat this?
Okay, no worries.
After
See,
after the T1,
yeah.
after the T, because I didn't understand the 0 1 0 concept.
Okay, 0 1 0. Okay, see, what it is going to happen is it will be yes, Vaikunt Vasan.
Sir, before deciding on one one and on two of the basis, that is, we can exchange rows.
You mean like this?
Ah, yes, sir.
Yes, yes, we can. Yes, we can.
Okay.
Just a second. Yes, yes, yes. We can change rows. Row transformation is allowed. Okay. So see, Lawrence, you asked it, right? So what happens is they will, when I say that this is my transformation, okay, and this is my transformation matrix. Okay, so we learn a new concept here. Okay, this is something that we cannot derive from what we have studied till now. This is altogether a new concept. Okay, you can take it like a fact because I cannot prove it in the session. Okay, you can take it like a fact that inside the transformation matrix, this is my transformation matrix, right? This is the matrix that we have been talking about. The first column is the linear transformation of the first ordered basis. The second column is the linear transformation of the second ordered basis. The third column is the linear transformation of the third ordered basis. Okay, this is a new fact for you. I have not derived it in this class. Okay, and I'm not going to tell you the intuition also. Okay, so this is the transformations. Okay, now the question can be asked for from this also, that this is that for the vectors for this transformation v to w. Okay, I have the basis for v as this and this. Okay, there these are bases, and these are ordered bases. Remember, ordered bases. Okay, now here this is the first, this is the transformation of the first order basis. This is the transformation of the third ordered basis. Pay attention, this is at number 3. Okay, and this is the transformation of the second ordered basis. Okay, now what you have to do is you just have to write these transformations at their right places. Okay, you have to write this at their right places.
So these are
Okay,
given
and when you write this, yes, these will be given in the exam. Okay, so different types of questions, no, different types of questions will be there. If this is not given, then there would be something else that would be given from which you can find this. Okay, one such question we will take in 1 minute. Yes, Roshan, these are not in RREF, but you can convert it into RREF. When you convert it into RREF, this will become 0 0 1. This will, okay, should not be doing this, but I am doing this. You just change the order of these rows here. You will get 100, 010, 001. Okay, so that's it. All right. I hope RREF you know. I cannot teach RREF here, please. Okay. So this is Lawrence. This is clear how I made this matrix. Yes, Lawrence.
Yes, sir. Yes, sir. Thank you.
Okay, this is how we write the matrix of transformation. Okay, after this, any question that we can solve on matrix can be solved here. Okay, this is just a way of not telling you the matrix. Okay, now one more way there is that they will not tell you the matrix, that is by giving you explicit transformation. Okay, they will say the transformation of x, y, z is equals to x plus 2y plus z, z minus x minus 2y. Okay, they will tell you this, and they will say to the what do we say, ordered basis. Okay, this is the transformation. Sorry, T is a transformation from V to W. Okay, and ordered basis of V and W are 100, 000, 001. Okay, and then what you have to do is you have to find the matrix of transformation. Okay, so in this question what you will do is, we know that what is the first column, that the first column is the transformation of the first ordered basis, right? So what is the transformation of the first ordered basis? The transformation is 1 0 minus 1. How did I do? I just substituted these values here. I just substituted these values here. 1, no, how 100? Mudit, no, it would be 1 0 minus 1. There is x here. Okay, ordered basis. No, what order are we saying? First column. No, the first column will be, okay, 100 is the first column. Yes, yes, yes. The first, this is the first ordered basis. Okay, yeah, yeah, correct. So you were talking about this. I thought you were talking about this. So this is 10 minus 1. So this will come as the first column here. What will be the second thing? Second thing would be the transformation of the second column, the second ordered basis. That is the transformation of 0 1 0. What is this? This is 2 0 2. Okay, this will come here 2 0 2. Okay, let's go forward. What is going to be the third column? That will be the transformation of the third ordered basis. That will be 1 1 0 1 1. That's it. This is the matrix you have. This is the matrix of transformation. Now you can easily find from here. You can find the null space. Okay, you can find the nullity. You can find what can you find? The 1 1 on. Okay, just a minute. Vaikuntavasan. Sorry if I pronounce your name wrong. Okay, so once you get this, is how they will hide you that this will how they will hide the matrix from you. Okay, but you can calculate it. Sorry, using this approach. Okay, so I told you two very common approaches by which the matrix is given. First is they give you the transformations themselves. Second is they give you the matrix. They give you the explicit transformation. Okay, this is called the explicit transformation. Okay, now one more thing. From here you can be asked, from here they can say, from here find this explicit transformation. They are giving you this and they will say find this. Okay, that also you should be able to do it. Okay, yes, Vaikunt.
Sir, we can use the basis matrix to find the nullity and mapping also, right, sir? 1 1 on 2 objective.
What basis matrix?
This one, order base, this one.
From how will you find? How will you find from here the nullity and all?
Okay.
No, I'm asking you. Okay, I'm asking you. Which approach are you talking about? I don't know. I don't think that.
Oh, I thought
We
these are this. Okay, okay, sir. Okay. These are the input vectors.
Yes, these are the bases of the input vectors. Okay, these are the bases of input vector.
Okay, sir.
Okay, they are not the. If you think that this is the null space basis, no, these are not the null space basis.
No, I thought that is the RREF and then we that was.
No. Okay. So this is here. Okay. Now from week 6, yes, Mukesh. Mukesh,
Hello,
hello.
sir. There is a standard basis always.
Yes, yes. No, 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 no. Not always. Okay. It is their wish and will whether they want to give you the standard ordered basis or whether they want to give you something else.
Okay, sir.
This is a standard ordered basis. This is standard ordered basis. Okay. If they give you this, these are just standard basis because the order here is changed. Okay. So they can give you anything. They are free to do. They may not even give you standard basis. Okay. Now from week 6, okay, what will happen is, okay, I gave you uh, a matrix. I gave you a situation where the input bases are different. Okay. There can be a question where output bases are also different. Okay. And this case I will not take here. Okay. The reason is that it is a very lengthy topic, and more important than that, it is a little confusing topic. Okay, and I don't want to take this topic just a night before the exam. Okay, so if you have already done this thing, congratulations, you have done the part which most students do not do in quiz 2. Okay, and if you have not done this, then don't worry, most people do not do this in quiz 2.
Sir,
Okay,
come again. Which topic, sir? I didn't.
this see here in this is not standard basis, right?
Yes, sir.
Okay, so and this is the input space.
Yes, sir.
So I have given you a input space. I have given you the input space which has different basis, non-standard basis,
Yes, sir.
right?
Yes, sir.
And they can give you a output space which has even different matrices, even different bases. Okay.
Okay, sir.
Okay, so they can also give you this thing. Okay, they can give you where both of them are different.
Okay, sir. So we
Okay,
have to find the transformation function.
yes. So here I took a question where the input bases are different. Okay, I did not take a question where output bases are different. Okay, the reason
Okay.
is that it is a little tricky and it is not appropriate for the last night.
Sir,
Okay, that is
output
why I'm
bases
not
are
taking
unique.
unique. What do you mean unique?
In particular input basis.
No, 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 no. There is nothing unique here. They can give you anything. Okay, see, this thing I created myself. Everybody is free to create their own bases as long as you know how to create bases.
Sir, scroll up a little bit.
Sorry,
Sir, can you show that again?
what?
That input matrix.
Yeah.
It's
Yes,
just
that is the same.
plus
Sorry,
3 and
sorry.
minus 3.
Hmm?
Yeah, plus 3 and minus 3, sir. Like 3, 7,
Plus
8.
which one are you talking about?
Second column, if I add a matrix with 3, 3,
Okay.
3.
Oh, okay, okay, okay. Yeah, yes, that was wrong. That was wrong. That was wrong. Yes. So if you are talking about this thing, that this cannot be basis. Yes, this cannot be the basis. Yes, this was wrong. Okay, they cannot be basis because they are standard. They are multiples of. They are dependent, linearly dependent.
Okay, sir.
Yeah.
So
Thank you for
let's get
catching this. Sorry.
so please tell about the kernel thing.
Yes,
And
this is the topic I am coming to right now. Okay. Yes, Dweep, the this what I was talking about is where domain and codomain basis both are given. Okay. And in fact, this topic will come in equivalence and similarity also. I will not take that there also. I will only tell you the equivalence and similarity thing. The domain codomain basis that I will not take. Okay. Not appropriate for discussing last night. Okay, now the next topic and the last topic we will be talking in week 6 is, and it is a very important, extremely simple is kernel and image. Okay, all those who have been in my session since the beginning, okay, I just spent 1 hour telling you that linear, not telling you, showing you that linear transformations are kind of equivalent of functions, right? Now these are exactly the same. So this is not the same here. This is the same. Image is just the same thing. Okay, let's. I mean, this would be very easy to understand. Okay. Okay. Now, what is a? This is a linear transformation here. Okay, let me draw it easily in a good way. Okay, this is kernel and images. Okay, now what is kernel? Okay, before coming to what is kernel, let me tell you how to draw linear transformations. Okay, if you remember earlier I said drawing linear transformation is difficult. Okay, and here also drawing linear transformation is difficult, but we will try to do something that will make a little sense. Okay, this is exactly the way we drew functions there. Okay, so this here, sorry, here this is, let me call it this vector. Okay, and
circles, interlace.
sorry. Okay, and this is the linear transformation. Okay, now kernel is all set of all points whose uh, transformation is the zero vector of output space. Understood this thing? Try it. First understand this thing. And then try to remember that I talked about this thing somewhere in this discussion. Try to remember where was this part.
Null space.
Yes. This is null space. Okay, for others also take 2 minutes to understand this thing. Okay, yes. So this is just null space. Okay. Earlier I wrote that this is the set of. Okay. Let me go up a little. Let me go up a little. Here, 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 here. Okay. Here I wrote that this is null space of matrix A is set of all vectors x such that the output vector is zero vector. Okay, this is exactly the same thing. Okay, now the differences that are here is that I am talking about something for a transformation. Okay, there is no matrix in discussion, there is a transformation in discussion. Okay, so and that is why here we get a zero vector of the output space. This is the only difference that we have. Okay, now why is there a difference? Why do we need another word here, kernel, when we actually have a word null space? Okay, the reason is very simple. The reason is very simple that null space is used for a matrix and kernel is used for a transformation. That's it. No other difference here. Okay, they are exactly the same thing. Okay, and it should be very simple now. Okay, and the question that can come here is what is dimension of kernel that is simply nullity. Now you know the reason why. Understood? This is kernel. Okay, now let's come to images. Images are even simpler than kernels. Okay, images are even simpler. Okay, I will just say one word. Okay, tell me how many of you remember this. What is that word? Uh, range. Range of a function. Range of a function. Okay, so how many of you remember this word? These are exactly the same thing. Image is just the function. Sorry, image is just the range of a function. Okay, image is set of all vectors in output space that have pre-image in input space. Okay, now you can see that I have put pre-image in braces in the inverted commas in quotations here, because pre-image is not the word we use in linear transformations. Okay, but I don't want to overcomplicate this thing. Okay, but the meaning is exactly the same. Okay, now just let me draw this, an equivalent of this diagram for image also. Okay, let me draw it here. This is V, this is W. Okay, and here we have let's say these are the dots here. Okay, and here we have yellow dots. Okay, and here there are blue dots. Okay, now these blue dots, sorry, now all these blue dots are inside this pink dots. You can see what I'm trying to do here, right? Now these things, okay, let me, this part, okay, this is too big, this part and this part, they don't have anything inside this part. Okay, there is nothing here that is connected to these things. Okay, so this is what I'm talking about, that this part, this pink thing, these are called image of T. These are called image of T. and this is transformation. This is it. Okay, and one thing that will be asked is, what is the dimension of image? Okay, it is equal to rank of A. It is rank of A. Okay, now for the kernel, it was obvious that it is nullity, because I already proved that this is a null space only. But here I'm not going to prove why this is equal to rank of A. Not the night for that discussion. But you can just understand that, yeah, there is something happening there which makes this dimension of image to be equal to rank of A. And what is A here? This is the transformation matrix, or this is also called matrix of transformation. Okay, is this clear? Okay, this is the end of week 6. This is the end of week 5 and 6. All right. Now we will take 5 minutes break. Okay, after this we will start week 7, and what will come after 8. Okay, week 7 and 8 we will do.
Yes.
Okay, Jivan Raj, we will talk about it later. Okay, then we will now we will start week 7 and 8. Okay, now this took 2 hours. Okay, this was kind of what I expected. Okay, this, I think it should be finished in 1 hour. If the week 8 part, if the part of projections and the later part, what comes after projections,
Empirical.
Gram-Schmidt process. If Gram-Schmidt process does not take more
Yeah.
time, this should be finished in 1 hour. Okay, so let's take 5 minutes break. Okay, and then we will start again. Okay. For the slides, Lawrence, I will share this with the members of the Kaziranga house, and then you can communicate them. Okay, so it's 7:02. Let's start at 7:10. Okay. Okay. Hello everyone. Let us start. Just a minute. Let me. Yes. So shall we begin? Hmm. Okay. Now week number 7. Okay. So what is the syllabus for week number 7? Let us first talk about it. Okay. I am audible to everyone, right? Yes.
Yes, sir.
Very good. Now for week number 7, we have three important topics. Three topics here. First is equivalence and similarity. Just a second. Equivalence and equivalence, equivalence and similarity. The second topic that we have is affine spaces, affine transformations. Okay, sorry, something happened. Affine spaces. And the third topic that we have is inner products. Okay, so wait a minute. Inner spaces. Okay, so here I will in this topic of equivalence and similarity, there is a topic for where we have domain and codomain. So just give me a minute, something happened with my tablet. Just give me a minute. Okay, yeah. So there was some issue here. Just give me a minute. Screen is visible, right?
No, not
The
visual.
screen is not visible.
Okay, so yeah, there is some problem happening. I don't know why. Just give me. Okay, let me call the organizers of the meet. Something is happening here. My screen share is not supporting. Just give me 2 minutes. Okay, so something happened in the settings here, and I'm not able to share the screen that way. Okay, so okay, thank God. Yeah, it started. Yep. Okay. Yeah. Yes. Okay. Yeah. Great. Okay. Yeah. Sorry for the disturbance. Now here in we were discussing week number 7 here, and in week number 7, what do we have is we have similarity, equality, equivalence, similarity, affine spaces, and inner product, not inner spaces, inner product. Okay, and affine spaces we will not be discussing today. Okay, affine spaces is an altogether separate topic. Okay, from the discussion that we are going forward with. Okay, it will need an altogether uh, different point of view to appreciate affine spaces. So I have decided to exclude this from today's discussion. Okay, now equivalence and similarity. Okay, so what is equivalence and similarity? Okay, first of all, what are we equivalent? What are we equating? Okay, we have matrices. Okay, and matrices they have different properties. Okay, they have multiple properties. Okay, and the different combination of these properties when they are present in two different matrices. Okay, when they're present in two different matrices, we call them equivalent. Similarly, another set of properties, if they are same, we call it similarity. Just like in real numbers, if we had let's say we had 1 and 3, okay, they both have certain properties because of which we call them odd numbers, because of which we call them odd numbers. 2 and 3, they have some properties because of which we call them prime numbers. Okay, and 3 and 5, they have such properties that we call them odd and prime numbers. Okay, and there are other properties also, we call them twin prime. So there are multiple different properties, and when they're present, when they're shared between two elements, we tend to give them a new name. And that is not just a part of nomenclature, that they help us in number theory. These properties greatly help in number theory. Similarly, such properties here in these matrices, they help us understand. Okay, so such properties, when they are similar between, when they're shared between matrices, we give them, we call them equivalent matrices, or we call them similar matrices. Okay, so what are these properties? Okay, what are these properties? Let's take equivalence. Okay, this is not equal. Okay, this does not mean equal. First of all, this is equivalence, an altogether different term. Okay, so equivalence means same rank. Actually, the definition of equivalence is very different from having the same rank. Okay, the definition of equivalence is that P. No, sorry. I don't remember what professor used in the sessions. A and B are equivalent if we can write A is equals to P B Q. Okay, where this and this, these are square matrices. These are square matrices. Okay, this is what we mean by equivalence. Okay, and this, an important distinction will come between equivalence and similarity is that A and B can be rectangular. Okay, and the similar matrices cannot be. Okay, they are definitely square. Okay, now this is a very difficult condition to check here. Okay, this is a very difficult condition to check. P and Q can be any matrix in the world. Okay, so this is how we define equivalence, and we found that A and B, if they have same rank, then they are then they are equivalent matrices. Okay, and there is one condition here: same order plus same rank. Same order plus same rank. If this matrix, if two matrices have same order and same rank, then we say that those two matrices are equivalent. Okay, another property that you should know here is, okay, first is this, second is this. Okay, and you can write it like this also.
Sir, by same order, what do you mean?
The A is m cross n and B is also m cross n. This is called order of the matrix.
Okay, okay.
Okay, now these are some properties which you should know. Okay, if I can write A is equal to P B Q, then I can write that P inverse A Q inverse is equals to B. Okay, and the right way of writing it is that B is equals to P inverse A Q inverse. Okay, and one thing which I nearly forgot here, that these are invertible square matrices. Invertible square matrix. Invertible square. Okay, now how can I get from here to here? It is very simple. Okay, I will quickly show this. Okay, A is equals to P B Q, right? Pre-multiply with P inverse. P inverse A is P inverse P B Q. Why inverse? Because these are invertible matrices, so inverse exists. Okay, now P inverse P is equal to identity matrix. Simple thing. That means it is equal to BQ. This is equal to BQ. Now post multiply with Q inverse, and you get Q inverse Q. Okay, this gets removed. What is left here? Just B. This is the same thing. Okay, so easy thing. Okay, now this is the second. This is one important property here. Okay, now one property you should know is A and B can they are A and B can be interchanged using elementary operations. Using elementary operations. Okay, so what is the idea behind elementary operations is that if I have a matrix A like 1 0 0 0, and I have a matrix B, this is 0 1 0 0. Okay, what is the rank of this matrix? The rank of this matrix is 1. Rank of this matrix is 1. What are the order? Order is 2 cross 2. Order is 2 cross 2. I have taken a square matrix. This is also valid for rectangular matrices. Okay, so these two are equivalent. Okay, these two are equivalent. Okay, now what do I mean? If I change column 1 with column 2 here, what do I get? I get 0 1 0 0, which is indeed the matrix B. Now similarly, when I do this thing, what do I get here? I get I get 1 0 0 0, which is indeed the matrix A. Right, so this is what elementary operations mean. Okay, now here the important catch is, throughout linear algebra we have been doing row operations only. Here column operations are also allowed. Okay, don't be confused. Okay, don't be confused. Don't apply column operations everywhere. Okay, this is a restricted place where column operations are allowed. Otherwise, do not apply column operations anywhere. Okay, so this is an important characteristic here of equivalent matrices. Okay, one last thing I want to talk about in equivalent matrices is that equivalence of matrices is a symmetric sorry is a transitive array, is a reflexive relation, is reflexive, this is reflexive, symmetric, and equivalent. Now sorry and transitive. This is a great source of confusion. And equivalent, equivalency of matrix is equivalent. Now this is very confusing. Okay, now pay attention to this thing, that this is from linear algebra, this is from linear algebra, these terms are from set theory. Okay, this I have seen many people suffer with this. What is this? These are from set theory. Okay, what is reflexive? Reflexive means A is equivalent to itself. Okay, symmetric means if A is equivalent to B, sorry, this is written very shabbily. If A is equivalent to B, then B is also equivalent to A. Okay, transitive relation is if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Okay, and what is the equivalent here? This equivalent, please don't be confused. This is different equivalence. This is a different equivalence. This equivalence means that all three reflexive, symmetric, and transitive behavior is true, is obeyed actually. Okay, I have explained it here for equivalence of matrix. This is similarity of matrix is also equivalent. Okay, it will come later, but the meaning is exactly the same as this. Okay, now here is there one last discussion that is left here is for the ordered basis in domain and codomain. Okay, this I am not doing. Okay, this I am not doing. I'm just telling you that this is also a part that is left. Okay, moving forward, this is everything from equivalence of matrices. Okay, if they give you two matrices, okay, if they say that these are two matrices, 1 2 3 4 5 6, and they give you a matrix 1 1 1 1 1 1 1 1, and they ask you whether these two are equivalent or not. Okay, first thing you have to check is the order should be the same, and then the rank should be the same. If both of them are true, then they are equivalent. Is the order same? No, so this is not equivalent. Okay, straight away cancel. Okay, let's remove this also. Now let's make the order same. Okay, is the rank same? Okay, what is the rank of this matrix? The rank of this matrix will come out to be 2. Okay, you can check for yourself. The rank of this matrix will come out to be 1. Okay, therefore the order is same but the rank is not, therefore this is not equivalent. This is not equivalent. Now let's make a little change again. Let's make one more change here. Okay, this, now you will check that this rank is also 1 and this rank is also, oh, sorry, this rank is also 2 and this rank is also 2. Now the order is same, the rank is same, and these two are equivalent matrices. Okay, is this clear? Okay, now let us quickly move forward to, we are running late. Okay, let us move forward to similarity. Okay, I'm going to copy this everything because similarity is going to have almost everything. Uh, yes, Vekun.
So that P and Q, like how to find that?
B and Q, it's not easy to find. It's
Okay,
not
sir.
easy to find P and Q. In fact, this is the reason why whenever somebody asks us to find the equivalence, we use this way, not this way. Okay. This is not even easy for mathematicians to find. Okay. Not just students, but for mathematicians also. Okay. This is difficult for everyone. Okay. Now, what is similarity? Okay, I'm going to make changes here only. It will save time. It will save time. Similarity. Okay, now it is A and B, they are only square matrices. They are only square matrices. Okay, what will be the change in the equation? The change in the equation will be P inverse. Okay, earlier we had Q. Now here we don't need two separate matrices. We just need one matrix and its inverse. Okay, now the change here would be just substitute Q inverse with P. Okay, see how similar things are here. Okay, now from this thing is again the same. This part is the same here. Okay, all we have to do is we just have to remove equivalent and keep adding similar. Okay, this is equivalence. This is just similarity. Okay, is this causing confusion here? Are you able to understand this thing?
Yes,
Yes,
yes, but
yes.
Okay, so this is similarity is also an equivalent relation. Okay, so again the same thing. This similarity is coming from linear algebra. This is a part of linear algebra. Navya, which part? And this equivalence is from set theory. Okay, yes, Lawrence. Navya, you
if
can
you
unmute
like,
also.
yes, like set theory, we can use in set theory easily. But how we can use these topics like reflexive, symmetric, and transitive in matrix? Is there any example of that type of question you have?
Yes. Okay. See, that will drag this discussion into a very wrong direction. Okay. I mean, not a wrong direction, but for the exam point of view, it is not a good direction. Okay. If you see this thing, I wrote A like this. Okay. That means A is equivalent to B. Okay. But I can also write this from here. I did this derivation earlier. Also, the same derivation will happen here. Okay. This means B is also equivalent to A. That means A, if A is equivalent to B, then B is also equivalent to A. Right? So that means this definition is, oh, sorry, we were in similarity, right? So this is similar, symmetric relation. Hai. Right? This is a symmetric relation. So where do we use it? That you can leave for this part. Okay. Otherwise, if you understood what it is, that is more than enough for this session.
Yes, yes, I
Okay.
understand that what it is, but I am just asking about how we implement this in a matrix.
uh, I cannot teach this here. Okay, this will take a lot of time, and plus,
Okay, okay,
this session is
okay,
not meant to cater this. Okay, I hope you understand
okay.
that, right?
Yes, yes,
Otherwise,
thank you.
I never say no to such questions in my sessions. Okay, but I usually take this at the end of the class, but today, not possible at all. Yeah, Navya, go ahead. Navya saying something?
Yes. R is equal to 2, right? How is that?
Hmm.
Am I audible?
Yes, 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 yes.
You derived R is equal to 2, right?
Huh? Yes, right.
How was that?
Because I calculated the RREF, no?
Sorry, there was distraction.
I found the RREF of these matrices.
Okay.
Okay, now
Okay.
how I did it so quickly without doing it is because this and this are not multiple of each other.
Yes.
Okay, if they are not multiple of each other, then this row will not become zero.
Okay.
Okay, earlier my matrix was like this. Okay, these
Yes.
two rows are multiples of each other, that means one of these row can become zero.
Yes.
Okay, now here the only change I did was make it 2. Okay, now they are no longer multiples of each other, therefore the rank is equal to 2.
Okay.
Okay, so this is only true when you have two rows or two columns.
Okay.
Okay, if
Okay.
it is more than 2, okay, then you cannot do it very simply. Okay, then there are other things also in action. Okay.
Oh,
Okay.
thank you.
Yes, Avni. Yes, if A is equivalent to B, then B, then if A is equivalent to B, then B is also equivalent to A. Yes, yes, yes. Same rank, then they are same determinant, same trace. Okay, there are more things here. Okay, this is not complete, there are more things here, but this is all we have studied till now. Okay, so for similarity you have to check these things. First, there should only be a square matrix, that is m cross n. Oh, sorry, m cross m. Both of them should have same order, they should have same rank, they should have same determinant, they should have same trace. Okay, there is something like same eigenvalue. Okay, we have not studied the concept of eigenvalue, but professor mentioned in his session, so I am also mentioning it here. Okay, but there are more things here. Okay, other thing is that which is very important here is all similar. Okay, sorry, not like this. If A is similar to B, then A is also equivalent to B. This is the same thing, but I'm not writing it in the right way. I cannot. If A and B are similar, then A and B are also equivalent. This is the right thing which I wanted to say, that if A and B are similar, then they are also equivalent. How can I say? Because for equivalence, what do we need? For equivalence, we only need this thing. Okay, so and this is also true for similarity, that is why they are equivalent. Okay, and if they are equivalent, then A and B can be interchanged using elementary operations. So this thing is true for similarity and equivalence also. Sorry, Sudeshna, I cannot explain that again. I have already discussed one and onto transformations. The session is available on YouTube. You can refer to that part. Okay, but I'm sorry, I have to move forward. Okay, we are already running a little late. Okay, this part is clear. Okay. Uh, yeah. Now, your trace means the sum of diagonal values. Okay, this is sum of diagonal values. Sum of diagonal values. Okay, very good. Now, one fact I want to tell you is uh, a scalar matrix is similar to only a scalar matrix. Okay, this is asked in many different ways. No, Mudit, there are these are two different sentences. If A and B are similar, then A and B are equivalent. Yes, this reflexive, symmetric, and transitive. This is not a property of matrices. Okay, this reflexive, symmetric, transitive. This is, you do not say that a matrix is reflexive. This is for a relation. Okay, I'm sorry, I want to go into depth of this, but I cannot go any more detail on these topics. Okay, so this is an important fact which you should know, that a scalar matrix is only similar to a scalar matrix. That is, if they give you a question to check whether this, sorry, whether these two matrices are similar, then you can say without checking that these two are not similar, because this is a scalar matrix and this cannot be similar to any other matrix. Okay, is this clear? Okay, now I have not mentioned the facts, but you should learn the facts like A and A transpose are similar or they are equivalent. Okay, these are such questions which you should check on the internet. Okay, so please check that which all special pairs are symmetric, which all special pairs are equivalent. Okay, otherwise also if you do not do that, okay, that if you do not do that, just remembering these would be enough. Okay, for similarity this, and for equivalence this. Okay, now quickly moving forward to the dot product here. Okay, the inner product. Okay, the inner product here, the inner product. Okay, inner product is how you define relationship between two vectors. Okay, up until now in vector spaces, okay, this is a very important thing to note. we have studied we have studied individual vectors. We have studied individual vectors. Okay, the only times we had two vectors was in addition. Okay, and that is also just individual vectors only. Okay, now we will be studying relation between vectors. Okay, this is for the first time when we will study two vectors together. Okay, this is the inner product. Okay, now there are some rules to check. Rules to, okay, before coming to that, what is, how you define an inner product? Okay, inner product is like, you have two vectors. Okay, these are, this is sorry, this is vector 1, this is vector 2. Okay, this is just a way of writing vectors, nothing else. Okay, this is vector 1. Okay, this is vector 2. Okay, you take these two vectors and you give out a real number. This is called a vector product. Anything that takes two vectors as input and gives out a real number as output is called inner product. Sorry, not yet inner product. Okay, this is just a relation here. Now there are some properties to be followed to be called inner product. Okay, this is just a product. This is just a product. Okay, inner product means some special properties. Okay, now for a product to be, for a valid inner product, for a valid inner product, there are four rules to be proved. There are four rules to be proved. Okay, now I will not prove those things. I will not take this part. Okay, I will not take up this part. Okay, I leave it to you all to practice yourself. I hope you have done it. Okay, it is exactly same as proving whether this is a given vector space or not. Okay, this is a valid vector space or not. This is exactly the same thing. There you proved it was a valid vector space or not using 10 axioms. Okay, here you have to prove it's a valid inner product using 4 axioms. Okay, if and only if all four of them are true, if and only if all four of them are true, then only you will, then only you can say that this is a valid inner product. All right, what are those rules? Please check this yourself. Okay, now I want to talk about dot product a little bit. Okay, dot product is a inner product. Okay, inner product. Okay, there are many inner products. Okay, there are many inner products. One of that inner product is called dot product. and one inner product is called dot product. And this is important. This is the most important inner product. Okay, let us discuss something about dot product. Okay, what is a dot product? Okay, dot product is written by a dot. Okay, and it gives out a real number. This is a real number. This is a real number. uh, how do we calculate dot product? Okay, and one more thing you should remember here is that okay, the vectors of same order. Okay, the vectors of same order. Okay, that means if v belongs to r2, then w should also be r2. Okay, you cannot do r2 versus r3 and r2 versus r4. These kind of things are not allowed in dot products. Okay, inner products here. Understood? Okay, now how do you calculate this? Let me write 1 2 3 4 5 6. Okay, this dot product can simply be written as, okay, dot product is simply v transpose w. This is v transpose w. Finish. This is dot product you need to know. Okay, I have a vector 1 2 3. I have another vector 4 5 6. I have to calculate the dot product between them. Okay, this is 1 2 3. Okay, this is the transpose. Okay, and remember one thing, we write vectors as column, right? We write vectors as column. Therefore transposing this vector will become, transposing the vector will become row matrix. 1 2 3 4 5 6. Okay, now it's simple. Multiply 1 with 4. Okay, this will be just 4 plus 10 plus 18, and this is equals to 32. 32? 122, yeah, 32. Okay. Okay, this is the dot product here. Okay, is this clear? Okay, now the important things from dot product are that v dot w is equal to w dot v. What is the meaning of this? This means v transpose w is same as w transpose v. Okay, see this 1 2 3 4 5 6. Okay, when I did 1 2 3 multiplied by 4 5 6, what did I actually do? I did 1 into 2, sorry 1 into 4 plus 2 into 5 plus 3 into 6. That is just basically multiplying this and adding, right? So this is why you write v transpose w or w transpose v. This is the same thing. Okay, this is the same thing. Okay, is this clear? Okay, this is very important from here. Okay, now one thing which you should know is, here is that what was that? Orthogonality. If this is a fact you should know, if v transpose, if v dot w is equal to 0, that implies v is perpendicular to w. It implies v is perpendicular to w. Okay, if they ask you whether two vectors are perpendicular or not, this is also called perpendicular or orthogonal. Orthogonal and perpendicular are the same thing. Okay, this is perpendicular or orthogonal. Okay, so this is how you can check. Okay, they will give you certain questions to do. Okay, one other thing which you should know is v dot w is written as, now what is this? This brings me to my next important topic, that is norm of a vector space. Norm of a vector. Okay, norm of a vector. After completing this, week 7 would be done. Norm of a vector. Now, norm of a vector is equivalent of saying length of the vector. Length of the vector. Okay, and this is single vector. Okay, this is not two vector, this is single vector. Now, the what is length of vector v? This is how we write length of vector v. This is equal to under root of v dot b. Okay, this is the length of the vector v. This is what we call as norm of vector v. Okay, what is norm? Norm is just the square root of the dot product. That is the square root of the dot product. Okay, is this clear? Okay, this is what norm of a vector is. Okay, is this understood? Are you able to understand this thing? Okay, now I'm trying to remind what is the next thing. Theta. This theta is angle between v and w. Angle between v and w. Okay, now let me tell you, let me just quickly do this. Let me quickly do this. I said if v is perpendicular to w, then v dot w is equals to 0, right? That implies company starting from here, this implies 0 is equals to cos theta. Okay, now length of the two vectors cannot be 0. Yes, exactly, Ryansh. This is what I just said, that norm is the root of inner product. Okay, this is what I wrote here. Okay, now coming back to this thing here. Okay, now here what we have is that length of the vector can never be 0. Okay, length can never be negative, length can never be 0. Okay, if it is point, only a point can have a vector, can have a length 0, otherwise no other entity has length 0. Okay, so this means this is not 0 and this is not 0. That implies cos theta is 0. That implies cos theta is 0, and we know that cos theta is 0 only when theta is equal to 90 degrees. Only when theta is equal to 90 degrees. And this is the reason why we say that v dot w is equal to 0, means that they are perpendicular. Okay, now this sums up the most important topics from week number 7. Okay, now I quickly want to rush to week number 8. Okay, week number 8. Okay, I'm running short of the time they have given me. Okay, so in week number 8, the important topics are orthogonal, orthogonal, orthonormal, projection, and Gram-Schmidt process. Okay, however, seeing that the time is running short, Gram-Schmidt process and projections I will not be able to cover today. Projections is sorry. What happened? Projections is one of my favorite topics to teach in linear algebra. However, I will not be able to take it now. Okay, I will end the session with a discussion on orthonormal. No, Avni, I have not discussed affine space. I was prepared not to discuss affine space. Okay, when I was planning the session, I knew that I could not discuss a few things. Affine space was one of them. Okay, the other thing was the in the equivalence of matrix, the codomain part. Okay, the domain, the ordered basis of domain and codomain. That part also I was not going to discuss, and I did not discuss that. but because of a little loss of time in the middle, okay, this projection and branching process I am not able to cover. Okay, now orthogonal vectors, okay, and sorry, just a second, orthogonal vectors and orthonormal vectors. Okay, these are just 2 minutes topics. Okay. No, Mudit, I don't think so. My time is already up. Okay. Let's go for orthogonal vectors. Okay. Now, orthogonal vectors is okay. This is a set of vectors. Okay. Avni, not that. Actually, you will get 1 or 2 questions from affine spaces. Okay, one to definitely. Okay, just quickly orthogonal vectors. Okay, I have a set of vectors. Okay, I will say that these vectors are orthogonal if all of them are perpendicular to each other. Okay, all of these vectors are perpendicular, then we say that this is an orthogonal vector set. Okay, and one thing here is, how do you check they are orthogonal? Simply, this should be 0 means that v1 is perpendicular to v2. Okay, now what is orthonormal set? Okay, orthonormal set means that first the vectors are orthogonal, that this is orthogonal first of all. Okay, then second thing is all vectors are unit length. All vectors are unit length. Okay, now what is the meaning of unit length? Okay, unit length means length is 1. Okay, this means that length is 1. Length is equals to 1. How do you check length is 1? Simple, I just told you in the previous slide that this means length of vector. This means length of vector. Okay, now what do we want? We want this to be equal to 1. We, sorry, not this. We want, therefore, this should be 1. Therefore, this should be 1. If this is equal to 1, and okay, let me write it for this set. For this set, ortho normal if v1, this is v1, v2, v3, they are orthonormal if v1 is perpendicular to v2, v2 is perpendicular to v3, and v1 is perpendicular to v3. Okay, first thing. Second thing is that the length of v1 is equal to 1, length of v2 is equal to 1, and length of v3 is equal to, okay, if you do this, if all these conditions are true, then our set of vectors is orthogonal or orthonormal. Okay, and the last thing that I will talk today is how to normalize a vector. Okay, how to normalize a vector. Okay, they will give you a vector. Okay, they will give you a vector 1 2 3. Okay, and what is the length of 1 2 3? What is the length of this vector? This is uh, the under root of the dot product. Okay, now what is the dot product of these two vectors? This vector would be 1 2 3 multiplied 1 2 3. This will be equal to 1 plus 4 plus 9, which is equal to 14. Okay, which will be equal to 14. Or let's not erase it here. Let's write this is equal to under root 14. Okay, so the length of this vector is 14. Sorry, under root 14. But we want this length to be 1. So what will I do to make it length 1? I will divide all the coordinates by the length. Now this is a unit length vector. Okay, so what can I say? I can say that the length, I don't have space here. Okay, just a second. Okay, I wrote this thing here, right? I wrote this thing here, so I'm erasing it. Okay, how to normalize a vector? Okay, so to normalize v1, okay, or normalized version of v1, normalized version of v1 is equal to v1 divided by under root, sorry, divided by mod of mod of this actually, this is, I'm saying mod, this is actually norm. Okay, is this clear? Okay, so yeah, this is the end of the discussion I could have today. Okay, however, I wanted to discuss a very strong, I strongly wanted to discuss this projection section. Okay, this is usually my favorite part from week 7 and 8. However, we cannot discuss this today. Okay, I wish you all the best for tomorrow. Okay, GS process is easy. Projection slightly difficult. That is why I like this. But GS process is very easy. Okay, and I wish you all the best. Read the questions carefully. Remember one thing: the paper will not test calculations. The paper will test concepts. Okay, so. Yeah, just the basic stuff. Read the questions properly, solve easy questions first. Okay, and I have found that most people don't know the meaning of solve the easy questions first. Okay, so how do you know which question is easy or not? Before starting any question, just read all the questions. Okay, in the first 2 minutes read the question, and by reading the question you can understand that okay, this is the question from projections topic, my projections is very strong, this is going to be easy for me. Okay, otherwise you, if you think you cannot do projection, mark it as hard. Okay, if it's a question from dot product, okay, you know dot product is easy, mark it as easy. Okay, so in the first minute of the question paper, oh sorry, in the first minute of the examination, read all the questions, just read the questions, make a tally 1 2 3 4 5 6 7 8 to the last question, and mark this question easy, this question easy, make it easy medium hard. Okay, easy medium hard, easy medium hard, and then start that by solving the easy questions first, then move to the medium questions, then move to the hard questions. And you have multiple examinations tomorrow for many subjects. Okay, start with the easiest subject. If you have English paper tomorrow, start with English, try to finish it in 10 minutes. Okay, if you have computational thinking there, okay, you will not have computational thinking. Okay, suppose you have Python there. Okay, so start by finishing Python first, finish it in half an hour or 40 minutes. Okay, okay, anyway, so you get the idea what you want, what I'm suggesting. Okay, start with easy things. Okay, losing marks on hard things is way more satisfying than losing marks on easy things. Okay, the better thing would be that losing marks on easy things is more painful than losing marks on easy things. Okay, so anyway, you got the idea. Okay, and for those who are asking for the Gram Schmidt projections and all, I took a session last term, but I don't think that would be available to you because that is in the Google Calendar. Okay, you don't have it in your calendar. I don't think so. It is on YouTube, so there are multiple other resources as well. Okay, yes, not losing marks is the best thought. I do know that. We'll talk about this later. Okay, bye bye. Good night, everyone. Okay, thank you all for joining.
A big thanks to you, Prakhar, and to all those who attended the session. I hope this was very much useful to you and it was a good revision at the last moment. I wish you all the best for your quiz to exam. Hope each one of you excels. Well, with that, I'll be closing the recording. Thanks a lot for everyone.